Thank you. So, good morning, good afternoon, wherever you are. And thank you for inviting me for this keynote. TerraView is a climate SaaS startup where our main goal is to help our customers with vineyards and wineries better adapt to climate change using a data-driven approach. In my talk, I'm going to speak about four key technological innovations which are available today already. But in doing so, I will also highlight some of the challenges we faced and how we overcame those, if at all we overcame those. Maybe some of us in the audience may take some guidelines from our experience. You'll also get a glimpse of some of the upcoming features which we are bringing in the next couple of months. But I want to really emphasize that a lot of what we do today has been possible only due to availability of huge amount of data, but also enabling infrastructure at the right cost for us to process the data in a cost-efficient manner. So as I said, we are a startup. We are a fairly young company, and our product went live in the market only this year in May. But since then, we managed to acquire 170 odd customers, essentially vineyards from different parts of the planet. But France and Italy have not yet been covered so far, but we plan to go there next season, or maybe the season after. So far, we have 7,600 vineyard blocks, which amounts to approximately 17,000 hectares of vineyard under TerraView platform management. This is still a very small number compared to global area under grape plantation. For comparison, what we manage today is just about the total area under vineyard plantation in Switzerland, and Switzerland is a very small player in this ecosystem. So one question which immediately comes to my mind, or should come to anyone's mind, is why do we need to develop a solution for vineyards and winemakers in the first place? So unlike large arable crops such as wheat, maize, or rice, grape growing requires precise intervention at the right time in various phenological cycles. And since there are numerous phenological cycles, and some of them are with an extremely compact timeline, a data-driven decision naturally brings a lot of comfort compared to just doing things based on experience or intuition. Furthermore, climate-related challenges are now numerous. Every enterprise has to manage production, distribution, and capital in any given fiscal year. These aspects are true for vineyards and wineries also. But uncertainty in weather or climate, has made many of these things quite challenging for our customers. I give some examples. So insurance costs have skyrocketed. In fact, some of our customers don't even take insurance anymore. Short-term financing has become more expensive. Yields have become very unpredictable. Therefore, distribution and supply chain planning has become extremely difficult. Now, especially for grapes, which grows optimally in a very narrow temperature band and soil pH values due to climate shift, geographical areas of production are also shifting. And sometimes they're shifting as much as hundreds of kilometers, both northwards and southward. Moving into regions where distribution networks may or may not be existent. In such a scenario, service providers such as TerraView are making an attempt to provide key insights as early as possible in a season, allowing our customers to make adjustments in operations as precisely as possible. We in TerraView so far have been focusing on generation of a solution to help our customers deal with problems in production. And this is what will be the focus of my talk today. And we believe that what we have created is at a very interesting intersection of technologies such as Industry 4.0, agri-tech, and climate-linked solutions. So before going into more details, here is a quick summary of what we have done so far. Our platform handles numerous imaging solutions and derivatives, We allow yield forecasting, traceability, and diagnostics through our VINECLICK application. And we also help our customers optimize irrigation in their vineyards. All of this is powered by data, as I said before. We work with data coming from numerous sources, from satellite constellations coming, which are operated both publicly and privately. Numerous IoT sensors deployed in the fields, local and regional weather service providers, as well as in some cases, high resolution drone survey data, which complements the relatively lower resolution data that we get from satellites. Hyperspectral is still highly experimental in TerraView. And one thing to keep in mind is that we choose data sources extremely carefully, thinking about whether our customers can afford it or not. So a lot of our decisions are governed based on a very fine balance between need, desire, and commercial viability. The next slide before this will be the last slide on TerraView, and then I'll go into the technical details. This slide captures the overall impact we aim to create. So, for example, through overhead imagery, we allow our customers to get insights on canopy cover, help them optimize planting and replanting decisions. We also help them with weed assessments. So we are able to do 3D models of the vineyard using high resolution RGB footage, and then doing height analysis differential. We are able to differentiate vines from wheat, for instance. Another example is yield estimation, which in turn has a significant impact on labor management, procurements, distribution planning, and so forth. So I'm not going to go into all of these significant impact areas because they should be self-explanatory. Now, if I want to summarize TerraView in terms of technical numbers, we deal with already more than 2.5 terabytes of data. We already have more than 72 million records into various databases. And on a daily basis, our database entries increase by 250,000 new records. We use a lot of industry leading solutions, both from open source and also rely a lot on capabilities provided by various public cloud operators. So we follow very stringently DevOps best practices inside TerraView, and our deployment strategy is first and foremost driven by the virtual infrastructure being managed through infrastructure as a code. And then we have 3 environments: development, staging, and production. All of these are, all the software and services deployed in these environments are managed through multiple CI/CD pipelines. Many of the virtual machines are dynamically created, although there are some static core services which are always running. We will see a bit more into the architecture in my talk. Here is a snapshot of some key parameters from our production environment, and this comes from yesterday. The monitoring graph on the right shows CPU load because of some periodic calculations which provide inputs to our rule engine. This looks quite nicely and well spaced, but sometimes these graphs don't look disorganized. So sometimes there is a lot of chaos in our production environments. So here is a very high level representation of the architecture which powers the TerraView platform. The entire development strategy is cloud native, and we follow the microservices design principle as much as possible. Our solution is event-driven, asynchronous processing mostly, but we also do batch processing wherever it makes sense. Everything inside TerraView is API-driven. Each box that you see here in this slide itself is a collection of smaller microservices, but using the same development philosophy as at the high level. Primary languages that we have used in TerraView core so far are largely Golang and Python. because they result in very small footprint microservices. If you look into the elements of the architecture, it would not be surprising. These are standard elements, authentication, authorization, access control. We have different type of storage systems for taking care of key values, for structured data as well as unstructured data. We deal with a lot of geographical data sets. So we have GIS extensions to some of our data management solutions. The data coming from sensors on the ground are time series in nature, so they go into time series data structures. And we use object storage when we have to give access to external vendors to dump data to us. So if I proceed next, so why have we chosen in an asynchronous approach? Because we have been seeing a huge amount of variability in processing times in the backend systems. Also, many times the data which we work upon, we don't know a priori when that data will be available to us. For instance, take an example for satellite tasking. We want to do a survey over a particular region. We give a tasking order to the satellite operators, but because we have a very stringent acceptance criteria, such as angle of inclination, cloud cover, daytime, nighttime, etc., there is no guarantee that the data is immediately available to us in next couple of days. Sometimes the satellite operator even takes 12 to 15 days before the data is made available to us. So everything is event-driven. Whenever something comes, events are generated and they're sent over RabbitMQ messaging systems. Why RabbitMQ? It's a quite well-known and mature technology component. It supports multiple priority queues, which fits perfectly our use case. And that's why we took the decision to use RabbitMQ in our systems. Some of our processes are long-running tasks, but some are periodic and scheduled. So we actually have a single time-based scheduler because doing a centralized control keeps our operations as well as our architecture a bit sane. I want to take an illustrative example of event-driven processing through an example through the lens of our image processing pipeline. So we work with a lot of external vendors because we ourselves, we don't do ground surveys. We have partners in various regions that do it on our behalf. So imagine a drone vendor doing a survey into one of our client properties. They come back from the survey, they pack the data, they archive it, and then do a data dump to an S3 endpoint, which we make available to the drone vendors. So there is an S3 monitor which checks for file system delta changes, and in an event when there is a new file appearing, it generates a file upload event, which gets picked up by event processor, which then creates a worker virtual machine with the vendor playbook preloaded in it. And because we work with multiple hardware drone vendors, there are different pipelines which deal with either Sequoia sensors or MikaSense sensors or FLIR, for instance. So there are different nuances to each of these hardware, and depending on what data type is that particular worker VM gets spawned. The drone data set invariably contains multispectral data. So multispectral data analysis always happens, but some configurations also capture thermal data. And in those cases, if there is a need, the next worker is triggered through an event, which then processes the thermal data set. Once all the images are processed, they are stitched, then they are cropped to line it with the crop boundaries or the plot boundaries of our customers. And then the finished event is generated. Once the finished event is picked up by the calculation service, it picks up the post-process image and then does further analysis of the image. For instance, doing canopy cover analysis or updating the NDVI maps, which powers irrigation prescription maps, for instance. So it's just a very nice example of how we do everything asynchronous and controlled and hand it over through a bunch of events going through messaging systems. So how do we handle scalability? All of our services are designed to be entirely stateless, except Rule Engine. But even in Rule Engine, the state is mirrored in a database almost constantly. So because of statelessness of our services, parallelization and task dispatching is simplified greatly. And many of our worker nodes can take these decisions to spawn additional worker nodes at runtime, and on the basis of various other informations which are present in the customer plot configurations. Do we and how do we need to handle data synchronization? Actually, we don't have to handle data synchronization because by design, we made sure that none of our services work on the same data set at the same time. So we essentially minimized the need in our architecture to really care about data synchronization issue. We manage handover, as I said before, from one process to another through events using message queues. Now let's go into some of the challenges that we had to overcome. Since we are dealing with more than 7,000 blocks and we query for local weather stations every tens of minutes, even with the highest service tier with some of our providers, we were not able to cover all of our blocks. We were hitting the API limits extremely quickly. So what we did, we took a grid-based optimization approach to minimize API calls to some of our vendors, while still covering all of our customer block bases. So we use S2, which is a Google library, which essentially uses the Hilbert space representation of Earth, where any 2 points in Hilbert space is approximately the same distance away in real world on the surface of the Earth. And we chose the grid size of 2 kilometers because we used our own internal clustering study, and we found out that 90% of our customers' plots were within 2 kilometers of one another. And so using 2 kilometer really helped us scale and solve the problem quite efficiently. Another problem that we constantly have to face is the GPU limitation issue. Our public cloud provider, especially the region that we operate in, could not keep with our core demands. Even though we had sufficient quota for GPU cores, our provisioning requests would fail because actually there was a limitation on physical GPU cores available in that region. So there was no other solution, but we had to throttle our processing. We could explore how we could use serverless to resolve some of our bottlenecks. But my problem here is that most of the serverless providers currently do not allow GPU pinnings to various functions. Now, here is a very good example where there is a possibility where we could use some of the untapped resources which are available in large HPC centers in Europe as well as in global. But the only requirement would be that the access experience in these HPC centers be made comparable to what public cloud service providers offers today. Otherwise, it becomes very difficult for startups like ours to, in a meaningful way, engage with the public money-funded HPC centers. Another problem that we are still dealing with, we do not yet have a solution, but the the TerraView engineering team is working on it, is image co-registration challenge. We work with multiple vendors, and this leads to slight GPS inaccuracies, which, if we do not correct, leads to images shifting from one day to another, which is not a nice experience with our customers. One of the challenge for solving image co-registration problem is lack of ground control point in some scenes. But there may be some innovative ways where this can be solved. So we are looking into it. We don't have a solution yet. Let's move into one of the most sought after feature in TerraView, which is yield estimation. We developed a service for our customers, which generates a daily update based on evolving weather parameters, as well as the input we get from the satellite operators on an ongoing basis. So before going deeper into this, let me tell you what is the status quo in most of the scenarios. Yield estimation in most of our customers, before we came into the picture, was a very manual and time-taking and expensive process, where consultants would be hired to go in the field property, and they would do fixed sampling. For instance, they would sample every 10th vine in the field, do grape cluster assessment, classify them as small cluster, medium cluster, large clusters, sometimes even do berry counting, and also estimate what would be the target yield based on the number of seeds present inside each grape fruit itself. And so you can imagine, if a plot is a few tens of hectares large, such an exercise takes a week to 10 days easily. And so because it's a very human-centric, manpower demanding exercise, the customer cannot afford to do it multiple times. They normally do it once per season, and then they work with whatever estimate that the consultants give them. Now, the problem here is, with such a one-time exercise, any adverse weather event which happens after the estimation has taken place completely ruins the estimate. Imagine a hailstorm or a frost which happens on the property, then all bets are off. Whatever number that the consultants gave after doing an expensive exercise becomes useless. So what we did in TerraView is we used a machine learning approach, where we asked our customers to provide us historical yield data from last several years that they have. Some of our customers did give us this data. We combine the historical yield value with historical signals from satellites and weather data dumps to create training samples. Then we created a model out of it. And then we use this model to do inference based on the evolving weather envelope of the current season, as well as the signals we get from the satellites of the current season. This has been a constant continuous update process in TerraView. We started with one model size, which had 250,000 weights, to version 2 of the model, which now has 7.5 million internal weights. Because we largely deal with time series data streams, our models are essentially a recurrent neural network-based regression models. But because now we have such a significant internal weights in the model, the training exercise takes extremely long time. Now, our training runs now take 4 to 5 days, and sometimes such runs fail due to several reasons, including, for example, the node getting out of memory. So one issue which we are now looking into is, can we do checkpointing in model training to prevent total loss in such a scenario? I do not have an answer yet, but hopefully there is a possibility. This slide shows the distribution of training data, historical yield values, which our customers gave us. And so if you look into it, most of our customers were able to give us with yield information coming from 3 years in the past. But some customers also were able to give us data going back to 25 years in the past, which proves quite helpful in doing the training. So this is the yield prediction service training performance chart, where on the x-axis is the training epoch numbers, and the orange line essentially represents the mean square error trend for training, and the blue line is the mean square error in the validation. As you can see in the chart, you can notice that there is still no convergence yet on the chart lines, which means that there is a possibility of increasing the epochs to gain on the accuracy of the model. But because we have limitations on the GPU made available to us, and also because the training already takes quite a long time, we essentially took a decision to not proceed further and just limit the training to what you see on the graph. This essentially shows the accuracy of the model we got in the first season. Most of our customers were extremely happy with the accuracy, and some of our customers told us that the numbers were up to 98% accurate. Although it's not such a peachy scenario for everyone, there were customers also where the accuracy was not very good. But we found out that those customers where the accuracy was not good were the customers who did not provide us with historical historical yield information. So here are some of the challenges we faced during the yield prediction service training pipeline design. Customer data ingestion always is a nightmare. Data curation, quality control is always challenging. So we had to develop several internal tools to help the customer onboarding team to do validation and ingestion in an organized manner. We used Z-scores to define thresholds. Using those thresholds, we are able to generate and raise alarms if some numbers which are being ingested are, let's say, more than 2 Z-score value. Then we tell the customer success team that, hey, there is something fishy going on. Double check whether this number that you are ingesting is actually correct or not. Data diversity is always a problem. Union of input parameters to provide a solution that worked with all customers creates numerous challenges. We had to implement several layers of input harmonization, outlier detection, and then also based on the phenological cycle, we had to make a decision when to do the prediction cutoff, because after harvest is done, there is no point in continuing to show the estimates to the customers. The data that we work with have different granularity. Some data signals are with an hourly granularity, even sometimes tens of minutes periodicity. Some data signals have a daily granularity. The yield value is a yearly number. Then some of the plot properties are essentially constants. So we had to use a hierarchical approach in signal packing when we created the input training data sets. Also, some of the signals are unreliable. Sometimes the satellite data feed is non-existent because of cloud cover or for whatever reason. And so we had to also deal with signals which may or may not be available during training cycle and also during inference cycles. So everyone these days talks about ML ops. So if I have to take a TerraView spin on ML ops, in my view, this would be an internal tool which would free the data science team from model customization requests, which essentially comes from the customer success team based on the request of the end user. Such a tool, in my view, should also enable out-of-turn model training and also keep track of model training status and also the underlying infrastructure health status, which sometimes may be necessary to generate timely alerts to the SRE teams in case, for example, memory is running out. Additionally, I would also imagine such an MLOps tool to have checkpointing support where if a training fails because of the infrastructure lack of resources reason, it should be possible to resume training and not lose the entire training run, and thereby losing 3 or 4 days worth of computation. Moving on to the next feature, VINECLICK. It's a tool which allows our customers to detect diseases and nutrition deficiency in their plants instantaneously, with the solution entirely loaded in their smartphones and with no need for network connectivity. So essentially, we loaded multiple ML trained models to do vine leaf detection, which is a binary classification problem, vine disease and deficiency recognition problem, which is a multi-label classification problem, because on a single image, there may be multiple disease signatures present. And also vine variety recognition problem, which is a multi-class classification, because a vine could be of one type and not another. There was a significant challenge because the training data set was lopsided, as you would see here. The labels on the x-axis are short forms for vine types, and the second picture shows on the x-axis the distribution of the training label images for different disease and nutrition deficiency. For instance, you would see that our consultants in the ground who captured the training sets managed to capture mostly healthy leaves, but then there was mildew, powdery mildew, botrytis, etc., which had significant numbers, but then there were some other classes which didn't have enough numbers to be of statistical importance. So we had to augment these data sets to remove bias through various tricks like cropping, resizing, rotation, etc. This is a very simple inference pipeline showing how the system works for both vine type recognition as well as the disease and deficiency recognition. It's nothing out of the ordinary, but just shows the steps. So after pre-processing, the system detects whether it's a vine leaf or not. If it's not a vine leaf, then it stops. If it is indeed a vine leaf, then it activates two other models for disease and deficiency recognition as well as the vine type recognition. One is an argmax problem. So in vine disease and deficiency model, the classes are not exclusive, whereas in the VTR case, the classes are exclusive. So we couldn't find readily available training data set in the research community. So we had to actually spend a lot of money to contract consultants in various geographical regions to help us collect relevant training data sets. So that's one way we overcame the lack of training data in this specific case. Now let's talk about another feature, which is smart irrigation. So although every customer wants it, not every customer can afford the solution accuracy the way it is made available to the platform. So for doing the differential or differentiated irrigation prescription maps, we rely on signals which come from both satellites as well as from ground. So we use evapotranspiration signals plus NDVI and canopy cover numbers to estimate how much water gets lost because of evapotranspiration and how much needs to be replenished. But the problem is, even though the solution is quite timely because of everyone wants to be ecologically sustainable, 90% of our customers don't have such sensors deployed. So what we decided was for such customers who do not have the right sensors deployed on their properties, we take a sensorless smart irrigation approach. So it's purely based on optical and thermal remote sensing data, but it has its own challenges. Cloud cover creates interference. So we had to create our own solution to remove cloud cover to essentially increase the acceptance of the available satellite input for such solutions pipeline. The other problem here was that you get data from the satellites, but most of the satellites are only capable of providing coarse resolution data, and sometimes very noisy data. And then if you don't have the ground truth, then inferring what is the relative moisture content becomes problematic. So we took quite an innovative approach because we found out that the swath of the satellite is so huge, there was always a water body in the scene. So even if our customer property was a little bit further away and there was no water body in the immediate vicinity, we could look further away and we could always find some lake, some river, some pond, some ocean. And then we used that to ascertain the relative soil moisture content over our customer's property. So I already talked about cloud masking to improve the acceptance quality of the satellite images. And this figure essentially shows what a sample output looks like. The problem here is the resolution, but despite this low resolution, this is still a valuable input to our customers who don't have the proper sensors deployed on the property, as they can still see which part of the property is adequately irrigated and which part of the property is not properly irrigated, and they can take a differential irrigation approach even with such a coarse output. Here are some of the key performance metrics of the sensorless smart irrigation solution. We use Landsat 8 thermal imagery, which has a 185 kilometer across by 180 kilometer swath. And every scene is approximately 1.3 GB in size, but the processing time and callback only takes 2.5 minutes per scene. And the output size for that scene is 1.5 MB. The issue here is the resolution. The output resolution is 100 meters by 100 meters. So every single pixel or the GSD is 100 meters here in this case. Another problem that we had to overcome was lack of frequent revisits by satellites. As I already said in the past, previously, that some of our satellite operators take up to 2 weeks to give us the data, even if we task explicitly. We cannot afford to wait that long to power some of our solutions. We use NDVI, EVI, which are agriculture indexes. So in several of our algorithms, including the smart irrigation solution. But because of lack of satellite revisits, we don't get the signal that often, which makes some of our output signals stale. Although there is still some value to the output because we get data continuously from the ground sensors, because of lack of update in the canopy cover or the health level of the plant, because which comes from the NDVI signals, that becomes a problem. So what we did was we started investigating an alternative, which is called the radio vegetation index. It's an alternative to NDVI. But because it works with radio waves and not optical waves, it's immune to cloud cover. But there is again another set of problems here, because radio waves are quite susceptible to backscatter problem. Depending on the undergrowth on the property, many times the signal may not be that useful. So a radio wave is a polarized signal, and generally the RVI formula uses a fully polarized scene. But our engineering team was able to find an approach where we were able to work only with two polarizations, so vertical and vertical horizontal polarization, thereby increasing the acceptance of many of the scenes coming from the satellite operators. So I present one initial result. So this is still work in progress. This is one of the very first results we got from the RVI using the optimized solution. On the left, what you see is the same property that I showed before for the smart sensorless smart irrigation. You see in the picture, you can maybe probably see one block is fallow land. So there is nothing being grown there. And what we found out was in our output, we could very nicely track that fallow land, which essentially told us that we are in the right direction. So this is once this is integrated, we will have a much frequent satellite signals going into our yield estimation, into smart irrigation solutions, and a bunch of other solutions also. The initial performance metrics that we saw in the RVI solution was that the scene download 2 images of different polarization took a bit of time, was sometimes not always available, but the scene itself was not very big. It was less than 1 megabyte in size. Processing times were very fast, a few tenths of seconds. And the resolution was also much better with the Sentinel Hub signals compared to Landsat. It was 10 meters by 10 meters. So now I'm going to go into one very interesting challenge, which is an ongoing challenge. Most of our customers, they maintain their historical data and also current season's data on Excel spreadsheets. Some of them do it in handwritten notes. And because of also lack of standardized input schema and formats in this ecosystem, human errors are plenty. And because there is no standardized tool for maintaining data, many times data is incomplete. And so this is a problem which we do not yet have a solution in TerraView. But recently we have started to look into a possible solution using OCR as well as some image processing and AI ML approaches to identify some category of inputs from these diversified input sets. So now I have talked about 4 or 5 challenges that we faced and how we overcame some, how we could not overcome some until now. Let me, in my last few slides, take you through some of the upcoming features that we are working upon. One is a wine gap detection, which despite many people in our data science team telling us that we should take the AI ML approach, we decided to do a purely signal processing approach here. And one issue with AI ML approach was, many people say garbage in, garbage out, right? So if you don't have proper ground truth in your input training sets, you do not get a reliable model to do inferencing properly. And doing a proper input data set turned out to be extremely difficult for us. What that would mean is we take a post-processed satellite or drone imagery of a client property, ask someone to revisit the vineyard row by row, identify where the gaps are, track the GPS locations exactly where they are, which itself is a problem because GPS is generally not very accurate. There may be 4 to 5 meters inaccuracy, and then come back and accurately label the post-processed satellite images with those gaps. So it's extremely difficult problem to solve. So what we did was we said, okay, let's use a signal processing approach. We treat wine and no wine as different signals in the scene, and we used discrete Fourier transform and inverse discrete Fourier transform, and also included image luminance corrections to identify, to essentially separate noise from signals and then identify gaps in the signals. And then those gaps in the signal essentially turns out to be missing vines if the pixel width of the gaps are beyond a threshold signifying a gap in the vine itself. This approach is quite fast. It enables an on-demand processing and doesn't suffer from the problem of lack of input training data. The other upcoming feature that we are working on is risk assessment service, which uses a bunch of signals coming from public data sources. So ECMWF in Europe, NOAA in the US, and bunch of other public tracked indexes to create a risk profile for a particular region. And this is not yet live, but here is a very, very first representation of what such a system is able to do for the wine growing regions in the US, in the West Coast. And the importance of this risk assessment is once we're able to accurately categorize our customers into a particular risk category, we are able to, first of all, tell them what risk category they belong in, but also use this information to empower other services such as parametric insurance or optimize lending rates for some of our customers. So as I said in the beginning, that we started out working with a solution which solves only the production angle of a business. But very soon, we will also create solutions for helping our customers with the finance, capital, and also distribution side of the equation. Another problem which is going to come very soon to our customers is vintage scoring. So essentially, vintage defines how the season is, and it has a very direct correlation on the quality of the grapes. And so many times when you go and buy a bottle of wine and somebody says that it has a score of 99 or 100, it has a very direct correlation on the quality of the season itself. And we have been able to create an initial service where essentially if you simplify the entire problem statement into a mathematical equation, it would essentially be a function which takes in weather as an input and gives out a score, and the score is the quality of the vintage. And so essentially, in our case, the function is a deep learning model. Weather is the sequence of various weather-related signals, and the score is a vintage quality score, which is a number which varies between 0 and 100. And in the initial experiments, with the limited data sets that we had, the training exercise showed a mean square error of only 5% on the validation data set. So that's a very promising sign. We are going to combine this with some other vintage scoring algorithms to see if we can expand this a bit further. So that brings me to an end to my talk. I just want to reiterate that what I spoke just now is not my own creation. We are a team in TerraView, and so I just represent all the hard work that they did. And here are some of the people in TerraView technical team, and we all are geographically quite distributed. We are a remote first company with talent coming from Europe, US, Asia. So with that, thank you very much for listening to me, and I'm happy to take questions if you have some.
Thank you very much, Piyush, for this very insightful and topic spanning presentation. I think it was very nice to get an insight. So I would like to ask the audience to please formulate your questions. Just write it in short version in the chat, and I will give microphone to you, or raise your hand if you just want to talk directly. So while we are waiting, I would like to bring in a question that is related to the switch from academia to industry. So if you look at the topics that are dominating the sessions, the technical sessions at this conference, we see a lot on workflows and resource management and cloud functions. And then on the big data side, we see tools like Spark or Flink. And then your architecture is different. Now, is it different because you think you have a specific problem to solve? That is, you know, maybe there are different problems in all the industrial domains. Or do you see a need to adjust also the research topics that researchers are working on, because maybe the research topics are outdated compared to what is needed in the industry?
No, so I don't believe that what is being taught in academic institutions are outdated. I know, for instance, the curriculum that you have, Yusuf, in your university is very much aligned with the needs of the industry. I will say that, you know, the solutions you describe, Spark and such, would become a necessity for us in the future. As I said, the amount of data that we deal right now is, even though it's in few terabytes of size, it's not humongous. And also the amount of land parcel that we have, as I said, is basically representative of the amount of land we have in Switzerland in this vineyard ecosystem. So once we scale out and once we have 10 times more customers with 10 times more land parcels that we have to deal with, I clearly could see a limitation in our current approach. And now the other question that you asked me, why we chose the approach that we did, is pure pragmatism. We are a startup with limited funds. We need to create a solution and bring it to the market as quickly as possible. So whatever was the strength in the team, we adopted that strength to create a solution quickly and bring it out. As simple as that.
And let me follow up with an additional question. Towards the end of the presentation, you mentioned the limitations of GPS. And so a native solution would be to combine different satellite navigation system signals, especially because compared to satellite data, those navigation systems are for free, right? So you can easily combine, let's say, GPS with Galileo and with other satellite providers that, according to academic knowledge, we would assume the precision would be higher. Can you comment on that? I mean, if it's such a simple solution, you would certainly have looked into that, right?
So the limitation comes not because of us not looking into it. The limitation of accuracy of the positioning systems come because our downstream vendors are not capable of working with those. So we work with a lot of drone vendors because we ourselves are not a drone company. These companies, some of them have high precision accuracy devices on the drone itself, and they're able to give us very, very precise geolocation information, but most of them, they don't have it. Now, so we inherently don't suffer from a GPS issue. The problem comes because our downstream vendors don't have the capability or the financial means to work with multiple systems. Now, especially on the limitation of gathering more input data for gap analysis systems. Even if the scouts on the ground have the capability to very, very accurately pinpoint the location of the gap, it still remains a challenging problem of sending a person covering 10 hectares of land and then figuring out where the gaps are and then labeling the input image with the gaps. It just does not scale.
Okay, thank you for answering these questions. I'm not sure if there's a legitimate question or if we are being Zoom bombed, judging by the names and portrait images of people just joining now. So let me therefore thank the keynote speaker again. I think it was a very nice, insightful, also inspiring talk. And we will take some ideas with us, I guess, for future research. So thank you very much.